Hello guys, here comes a little explanation of a job you're going to do today. You're going to try 10 exercise like the one I will do. So here you have a little example of how these exponential equations behave. A little observation is that those behaves with the same base. Those are power expressions. You know power expressions like 2 to the power of 3, for example, or 2 to the power of 4, maybe. Those are power expressions, and essentially what we have in here, it's a number raised to an exponent. So we have the same over there, a number raised but not to an exponent. We have these raised to a variable expression, and the main idea is look for the way to find out the value of x that will help us to solve this exercise. Okay, so we'll do something and it's applied this important rule. If you have a at the power of x and a at the power of y, as you can see here, you can conclude that if those exponential expressions have the same base, then you can see they will have the same exponent. It's a pretty obvious thing. I mean, if I have 3 at the power of 4, and then this is 3 at the power of something, this something must be 4. I think so, because this is the only way we have those expressions being the same, being equal. So be careful with this property. Is useful just when we can work the same base. Question is, does 16, the power of 16x at the power of negative 3, x minus 3, and 8 at the power of x plus 2 have the same base? Well, that's the first thing we're going to do. It's identify if they have the same base. Essentially is this, identify the base. So what means identify the base? You can do something, and is that you can decompose the numbers in order to see how to write them as an exponential expression. In this case, 16 have a half, which is 8. 8 have a half, which is 4. 4 have a half, which is 2. And 2 have a half, which is 1. So essentially, we're saying that 16 can be written like 2 times 2 times 2. I mean, 2 4 times, which is 2 at the power of 4. Oh, wow. There is a base for 16. It means that we maybe have the same for 8. I think that yes. And if you see, we have over there the procedure. So let's decompose 8. And this is how you can start those exercises. 8 have a half, that is 4, have a half that is 2, have a half that is 1. So essentially, we are saying that a can be written like 2 to the power of 3. So that's what you will do. And in those kind of exercises is like the main idea of what I want you to do. So let's see how this exercise will go. Because right now, 16 and 8 are not the same, but if we make them be the same, then the exponents must be the same. So let's see how it works. And instead of work with 16, we're gonna work with 2 at the power of 4. And of course, this still being raised at the power of x minus 3, because the exercise is 16 at the power of x minus 3. But 16 is 2 at the power of 4. Something similar for the other one. In this case, we have that 8 is 2 at the power of 3. So immediately we're going to have, instead of 8 at the power of x plus 2, we're going to have 2 at the power of 3 at the power of x plus 2. So here you have power of a power. There is a property, don't remember it. Here it is, power of a power. And the main idea of a power property is that you have, for example, let me see. What about a at the power of m at the power at the same time of n? It is equal to the product of those exponents, okay? So you're gonna have a new power, but with the product of those exponents. It means that here we're going to have, well, the 2 that stays there, and the 4 times the exponent already there, which is x minus 3 equals 2. Something similar for the other one. That 2 already there, and the 3 times the exponent already there, which is x plus 2. Well, here we have something simple, and it's just solve those distributive property exercise. I think you know that. It's multiply the 4 times the x, multiply the 4 times the 3. So finally here we're gonna have 2 to the power of let's see those new values. 4 times x is 4x. 4 times -3, it's -12. Yep, there he is. And here we go with the other one. Well, something similar for the other exercise. So here we have 2 at the power of, well, let's write the equal. 2 at the power of, let's see, make a distributive property with this one. In a similar way, okay, we're gonna multiply the 3 times the x and the 3 times the 2. 3 times x is 3x. 3 times 2 is 6, okay? And that way, if you see, if you pay attention details, we came from different expressions, different bases, practically 16 and 8, they are different, but we look for the way to make them the same base. Now, is it possible every time? No, okay, no. For the exercise you're gonna try, it will be like this. But for these kind of exercises, not always like that. Suppose that instead of 8, you have 18. 18 cannot be written like 2 at the power of 3 or 2 at the power of something. Because 18 at the end is like 2 times 3 times 3, right? Decomposing in this way. But it's not something that you will have like the same base with the other one. So this topic is something we're gonna study on the next week. But this is like the first part of the equations we want to see. Something similar happens with logarithms, but right now we're gonna focus in this ones, exponential ones, because I think of the time and because they are pretty easy. Well, finally, if you pay attention details, I was saying, sorry, these expressions right now fit in this property. We have 2 at the power of something equals to 2 at the power of something. So here we have a at the power of x equals to a at the power of y. So essentially x equals y, which essentially means in our exercise that 4x minus 12, 4x minus 12 equals to 3x plus 6. Why? Okay, this property is telling you that. Practically disappear those powers, those bases, and focus just in the exponents. Why? Because they are equal. There is no other way. I mean, they stays the same. Must then identify the value of x that makes them be the same. So let's find it. And I think we have been solving equations with variables in both sides many times since 9th grade. So I think you're a master solving these ones. It will be pretty easy. All you have to do is work variables in one side and work numbers in the other one, as I show you right now. Okay, so what I did is pass the 3 to the other one, to the other side, and then pass the -12 to the other side. So finally here, working this expression, working the variable expression we have there, we're gonna have x equals 2. What's 6 plus 12? Come on, that is 18. And this would be the answer of the exercise, because that 18 will make those expressions have the same power, right? They will have the same power. As you can see here, 18 minus 3, well, you can check it. You can check it. 16 at the power of, in this case, will be 18 minus 3. It's equal to 8 at the power of 18 plus 2. Well, 18 minus 3, it's 15. So we're going to have 16 at the power of 15 equals to 18 plus 2 will be 20, I think so. Yeah, so 8 at the power of 20. In the calculator, we can check it. What is 16 at the power of 15? Well, it gives us a pretty huge number. It's a very huge number. And then what is 8 at the power of 20? The same number. Yeah, the same number. If you see, it's pretty huge, but it's practically the same in both of the cases. The same answer. Yeah, that's why it doesn't change. It's 1.15 times 10 to the power of 18. If you wanted 1.15 times 10 to the power of 18, it must be scientific notation because this number has like a bunch of spaces, a bunch of numbers. I think it's like, well, million, billion, it's like a trillion in this case, right? Where you have like many values. And I think for the 8 to the power of 20, you're gonna see something like this: 1.15 times 10 to the power of 18. So this will be like the way to be sure, next expression. Well, let's write again, 8 at the power of 20. Exactly the same, 1.15 times 10 to the power. If you see the same answer, this is something you can do just to check. So here you have it, and essentially that's what I need that you do. Important part of the procedure, make the decomposition of the number. That way you're gonna find out what is the same base they have, okay? So I appreciate a lot, guys, that you are trying and doing your best with those exercises. And I hope to see you soon too, okay? So see you, bye.